Okay, the next chapter is about Bayesian statistics, and the title of this segment is Lies, Damn Lies, Statistics, and Bayesian Statistics. Rolling the clock back when I was in grad school, back when we had computers that would take up much of a room, we were being taught to employ something called statistical data modeling. And the idea there was you'd start out with some sample of data, and then you'd try to fit it to a known distribution. You'd perform different types of tests, goodness of fit, significance tests, et cetera, to try to show that the data fit the distribution. That's a key point. So you do these tests to make sure that your data is fitting your model. And at that point, then, you really stop looking at the data a whole lot. I mean, maybe if there's some outliers, you go back in. But generally speaking, you make inferences based off of that known distribution with respect to the fact that you've proved it because of these significance tests. The long and short of that is that it's really great if you're doing a lot of drug trials or actuary tables or that kind of statistics, but it's not so great for making decisions in general. And we'll take a look at why. I like this phrase, ceteris paribus. I hope that I'm not slaughtering the Latin, but it translates from Latin into English as all other things being equal. And that notion gets invoked in terms of decision-making and judgments using a concept called isolation. The notion of isolation, there's a few different forms of this, but let's say that on the one hand, we could assume that other factors are fixed while considering a particular item. Or we could consider that other factors change so slowly that they appear to be constant. Or that the other factors just simply won't be affected by the item that's being considered, and it's therefore independent. So isolation is something used in judgment, and frankly, it gets used a lot in statistics, at least in that statistical data modeling side of things. But in contrast to this, if you go and look at, there's a great film, 1950 Japanese period drama by Kurosawa. It's called Rashomon, and it symbolizes a kind of tension that's been in statistics for a long time. It really cuts back to what Mark Twain was saying as lies, damn lies in statistics. And I pulled this great quote out of Wikipedia entry for Rashomon. The film is known for a plot device which involves various characters providing alternative, self-serving, and contradictory versions of the same incident. And that sums up a lot of data modeling in a nutshell. Looking at that old school way of statistical data modeling, judgments were based on frequency of events, assuming that events are repeatable and happening over and over. And we talk about this in terms of frequentist statistics, as a kind of a branch of statistics, if you will. However, I'll contend that when you're doing everyday business, decision making that you have to do day to day, that kind of isolation is actually a luxury. Generally speaking, the key factors that you have to consider, these are changing. And therefore, the decision processes that you have must be adaptable, and they must be kept updated. So let's consider an example about this. Okay, our test case, foobartender.io, been doing some work on the user interface. They've got 4 different user experience designs, and it's all about arranging the top 4 cocktails on a tablet display. Because you don't have a lot of screen real estate on those mobile devices. So people are going to look at the top row and they're not going to scroll down a whole lot. They'll go off and do something else instead of ordering a cocktail. So the problem is, based on how often customers have purchased drinks out of each of the 4 designs, can you tell which of these customer experiments has the lowest purchase rate? So we're going to try to find out which one's the worst. And down here we've got a table. We've got experiment 1, 2, 3, 4. And experiment 1 had 24 customer visits. 3 of those converted to be purchases. Number 2 had 180 visits. 30 of those converted to be purchases. And let's just push this a little bit further. Still on the subject of making judgments, not statistics specifically, but judgments in general. Let's push this question a bit further and say, okay, which customer experiment has the lowest purchase rate? That's the original question. Number 2, why did you give that answer? And number 3, how did you calculate it? So we're going to employ a little bit of our computational thinking here and actually try to reverse engineer it. I do this as an interview question. So here I'm giving away one of my interview questions. It's served well for a number of years, but it's now being sacrificed to a greater good. When this is an interview question, it's typically I'll say that it's an open book test. And the candidate is free to use a calculator, laptop, web browser, supercomputer, phone calls to any in-laws who just might happen to be Nobel laureates, whatever. But just don't take any more than 5 minutes. Just come up with an answer and be able to defend it. Now, the thing that most people do when they look at these 8 little numbers is they come in and they say, oh, okay, experiment number 1. Huh. Let's see. So experiment number 1, we've got 3 purchases over 24 visits. That's equals to 1/8. So, let's just take the fraction there, 0.125. Okay, and they go, okay, experiment number 2, that's 30 purchases over 180 visits. So, gosh, what does that come out to? 1/6. Okay, and so let's just round that down to 167. And then number 3, we've got 50 conversions out of 250 visits, impressions, whatever you want to call those. Okay, so that comes down to, gosh, I hope that's 1/5 equals 0.200. And then number 4, finally, closing in on it here, we've got 15 over 100 and 15 over 100. Well, let's see, if we divide out by 5, that's going to be 3 over 20. And that comes out to being, okay, so, people look at this and they'll say, well, okay, we took the simple ratios there, and if you compare all of them, clearly this one's the worst. Okay, this is the lowest purchase rate. So there's your answer. 5 minutes, done. But then again, some people will step back and say, well, you look at the sizes here, 24 versus 100, 250. This is like, almost an order of magnitude smaller. So this has less data points. Therefore, maybe this doesn't work. Maybe just throw it out. And frankly, in business, that's what I see. Working in advertising with looking at ad bid systems and doing that kind of analysis, that's actually what the decision makers are thinking. It's like, oh, it looks too small, let's just throw it out. When in fact, it may have actually been the best campaign you had. So a big idea here is that a reasonable solution to consider in this case of these 8 little numbers is that when you've got a ratio and you want to compare them, one thing you can do, it's called point estimates. And this gets into an area of math called intervals that there's far too much written about this. There's a lot of great stuff written about it, and you can really jump off the deep end. But I picked out here a pretty simple, useful case. It's called the adjusted walled method. There's a lot of other similar methods. Anyway, what we're trying to do is say we've got some estimate, we've got a ratio of a certain number of things that happened out of n number of trials. So we've got this ratio here, and that's going to give us some kind of value, and then we're going to bound it by some upper bounds and some lower bounds. Okay, so that's pretty interesting then. We can take a ratio and we'll come up with some way of saying, okay, well, what should this number really be? But then also put a confidence interval around it. Put upper and lower bounds around it so that you can know, well, we think it's going to be p plus or minus. Okay? And so that way you can start to make a decision. It's like, well, how do these all compare? Do they overlap with each other? And typically we talk about like a 95% confidence interval. That's just what people do a lot in the industry. You can adjust that if you want. It probably doesn't make a whole lot of difference in many cases. It's probably pretty good. But the important part is to actually have the confidence interval. So the way this is calculated is we can say that if we take p, rather than just taking a simple ratio, we'll take x plus 2 over n plus 4. And now that's pretty interesting because 2 over 4, well, that's the same thing as 1 over 2. That's the same thing as a coin toss, 0.5. Probability of a coin toss should be, if it's a fair coin, 0.5. And so effectively what we're doing here is adding the probability of a coin toss into that ratio. And one word for this is shrinkage. The idea is to kind of condition the ratio so that you don't get really wildly skewed estimates if you just have very small numbers. And then once you've got the p, you can go in and calculate the confidence interval, basically wrap it with upper and lower bounds. In terms of computational thinking, this is, in my opinion, this represents a kind of pattern generalization and abstraction. Looking at something that's a ratio, let's pull back up a little bit higher level and say, well, we can apply point estimates and confidence intervals so that we can try to mitigate the risk when we're making decisions based on ratios. And that will allow us to have near-term decisions. We can go in and look at a customer experiment pretty early and see, well, where's it trending? But we've got some bounds placed on it too. And this is really important when you've got processes that are being updated over time. So, cutting back to this, for foodbartender.io, we're looking at customer experiments, and ostensibly those are rolling in all the time. People are ordering drinks. You're looking at a snapshot in time of how these experiments all line up. And you may have one that hasn't had a whole lot of traffic yet, for whatever reason, and it may be trending really good, but if you don't condition the numbers, like I say, with a point estimate and confidence interval, you might inadvertently throw that out. And boy, have I seen a lot of ad tech companies who didn't do well precisely for that kind of risk, that kind of problem. This is really about a kind of temporal isolation. So by using the point estimates, you can avoid that kind of isolation. You can really take into account, you know what, this thing is changing. I don't want to throw the baby out with the bathwater. I don't want to make some kind of premature judgment that just doesn't have a lot of basis. So calculating the point estimates here, experiment 1, as it turns out you've got a ratio there, 0.15, upper bounds of 0.31, lower bounds of 0.03. Let me draw that a little bit on the board. Okay, having never actually drawn this before, let's do it by hand. So we've got 0, and we're going to range out there to about 0.4. And so let's say that we've got about a 0.2 somewhere there, and a 0.1, 0.3. So for experiment number 1, it's going to range from, let's see, down here. It's going to range from approximately there out to approximately there. And we think that it's centered right around 1.5. OK, so we've got this confidence interval describing it. We think it's right here, but it's actually, plus or minus. There, that looks a little more balanced. OK, number 2. It's at 0.7. That's a little bit further out here. But it's plus or minus 0.12 and 0.23. So it's a little tighter. OK. Number 3 is going to go here. Number 3, the ratio is at 0.20. But it's going to, the lower bounds and the upper bounds is going to range from 0.15 to 0.25. So that experiment is edging over a little bit this way. And then number 4, let's see, adjusted p is at 0.15, back down here. And it's going to range from 0.09, which is approximately there, out to 0.23. 3, about there. OK. So now you can see that these different customer experiments all kind of stack up. And you can see some of them are edging out further this way, which is ostensibly going out this way is better. You have a higher purchase rate. But when you look at the bounds, they all overlap. And in fact, this one down here with the least data points has the widest confidence interval. That kind of goes without saying. So it includes all the other tests. You can't actually distinguish which one of those is better or worse. And so as an interview question, the question that we asked was, can you tell us which one's worse? And the answer is no. But I've seen candidates, even executives that I've given this to at companies just to try to evaluate where they are in terms of data analysis. I've seen people argue. I saw one technical director sent a 2-page email about why the answer is yes, going into detail. But yet, you've got to take into account that things are changing and you have to condition it.